Colloidal.
Okay. So we've got a suspension, not a solution, because the particles are too large to stay evenly distributed throughout. A suspension will only keep those particles evenly distributed as long as you keep providing energy in the form of stirring or agitation. Okay, well... Okay, so if we take clay, and you can do this clayish soils too, if you have clay soil at home, if you dig a hole and you mix water into it, so you take clay plus water, you're going to get this cloudy chocolate milk or, pale tan looking, milky looking stuff. Will it settle out overnight? So we said the sand will settle out almost immediately. The mud water will settle out overnight. Is the clay water going to settle out quickly? No. Clay particles are very fine, but they're not that fine. Eventually, they will settle out. Eventually, clay particles will settle out. So when we take that clay and water, it will stay suspended for a while. For a while. The particles in a colloid relate to the particles in a suspension and the particles in a solution. Yeah, colloidal particles. So they're bigger than the particles in a solution, so they won't stay in solution. They will not stay evenly distributed. But they're smaller than the particles in a suspension. They'll stay there for a while. It'll take them longer to settle. And clay water is the classic example. If you've got really clay soils and you go out after a rain and look at mud puddles, you'll see colloidal suspensions in mud puddles. So because a colloidal suspension is not a solution, we can't talk about a solvent and a solute because those are features of a solution. What we talk about instead is the dispersing medium and the dispersed phase, or it's sometimes called the dispersed agent. So the dispersed agent or dispersed phase in our clay and water mix would be the clay. It's dispersed through the water. The dispersing medium would be the water. Okay. So one neat feature of colloids, and the way to tell if what you're looking at is a colloidal suspension, is this Tyndall effect, or Tyndale, or Tyndall, I don't know how you say it. Anyway, if you shine a light through a colloidal suspension, it looks cloudy. So gravy is a colloidal suspension. Shine a light through gravy. It's cloudy. You have all, I can guarantee, walked around or driven around in a colloidal suspension. What is it? Fog. So, gravy. Yes.
Driven in gravy.
So, your headlights in fog, that's the perfect representation of the Tyndall effect. And if you have seen that effect, where your light is all sort of scattered by the fog, that's Tyndall effect. Okay? And that's how you can tell if a solution is a solution or if it's a colloidal suspension. Make sense?
Yes.
Have you heard the term electrolyte before?
Yes, it's in Gatorade.
It's in Gatorade, it's in Powerade, it's in Pedialyte. If your baby brother or sister gets the vomiting and diarrhea, you're going to pump them full of Pedialyte to keep them hydrated. And wrestlers drink Pedialyte apparently during season, I hear.
I've never drank Pedialyte.
So, you hear about electrolytes. What are they? Okay. So electrolytes are free-flowing ions. Where does your body use calcium and potassium and sodium ions? Do you know? In all your cells. You have, in dendrites. So all of your muscular actions are really the result of electrical impulses flowing between cells. And those electrical impulses are transmitted through the movement of ions very often. So they're pretty important for you. Now, let's back off of the idea of electrolytes, and let's talk about sugar and salt. This is easy, right? So sugar, and it's a little bit hard to see, we've drawn a sugar molecule here. It's a bunch of carbons, hydrogens, oxygens, and more hydrogens. And here we've got a chunk of salt, which is just sodium and chloride ions all clinging together desperately out of mutual attraction. If we drop both of these into water, let's think about what's going to happen. So in a clump of sugar, if I hand you a cup of sugar, each little crystal of sugar is, I don't know, millions, billions of individual sugar molecules held together with intermolecular forces, right? Okay. If I hand you a chunk of salt, and we've got some salt up here, then each little piece of salt is just individual charged atoms, ions, clinging together. When we put the sugar into the water, will the molecules break up? How many of you say yes? How many of you say no? Okay, how many of you are too chicken to commit to a position?
I don't really understand.
Okay. Okay. Not break down when we put them in solution. They get separated from one another. It's like going to, the county fair with your family of 14 children, and you all get separated in the grandstands. They all get split up, but you don't lose your individual identities. So these sugar molecules remain sugar molecules, but they get separated from one another. Now, in the case of salt, we've got those sodium and chloride ions, and we're going to sort of enlarge the view of what happens with salt. Question. So when we put that chunk of salt in water, you have salt water. Except what you really have happen is the water gets in between all. Okay, so the water actually moves in between all of those sodium and chloride ions, and it separates them. So now, in that water, what we really have is a big pool of sodium ions and chloride ions. And yet that's salt water. But they are actually free-moving ions. So why do you think water can get in there and break up the sodium and chloride ions? No? What's so special about water? So the water, because it's a charged molecule, it's polar, can worm its way in between those other charged molecules, those ions, and it breaks them up and moves them apart. Now, this sugar water is a molecular solution. It yields molecules in solution. This salt water is an ionic solution. And when we've got all these little ions flowing around in here, that means we've got electrons that can move. So guess what? One of these solutions conducts electricity. Which one do you think it is? Yeah, salt water. There. Okay, conducts electricity. It's a terrible little lightning bolt. If you were to go bathing in a lake of distilled water, 100% pure water, submerge yourself right up to the tip of your little old nose during a lightning storm, shake your fist at the sky, you're going to be perfectly fine. So why do we stay out of lakes when it's lightning? Ah, interesting.
I thought it was just water in general.
I think we did.
I just thought water bad when
We call any solution that will conduct electricity an electrolytic solution. And so electrolytic solutions typically are composed of ionic substances dissolved. So salt water is an electrolytic solution. Pedialyte, would that conduct electricity? Would Gatorade conduct electricity? Yes. Those would be great conductors. So yeah, you could yes, there you go. You could use Gatorade as part of a circuit. So when I was just out of college, I worked for the Division of Wildlife, and I did fish survey work. I worked in the fisheries department. It was a great job. I got to be out on a boat for lots of parts of the day on early spring days and early spring evenings. And one of the things we did a lot of fish survey work. We counted fish, and we collected things from fish. And one of the things we did was electro-night fishing. So we would go out on a boat, and here's the boat. And on the front of this boat, whoops.
Oh, no more.
Oh, no, okay. On the front of this boat, there was a boom. So there was a big, long bar that extended out over the end of the boat, and coming off of that boom was this sort of figure-8 antenna-looking thing, and we had the water line, and dangling off the boom down into the water were these things that looked like, I don't know, some sort of nightmare curlers, and they were pieces of metal on wires hanging down into the water. Okay. So let me ask you this. What happens? Anybody here ever get shocked? This is electro-night fishing. You've got a boat, you've got a boom, you've got these crazy, weird antenna-looking things hanging out with these little crazy things hanging off them down into the water. And up here on the deck with these two people are two pedals. And these two people have to keep their feet on the pedals. And as long as they keep their feet on the pedals, electrical current flows out into the boom and down the wires and out into the water, creating an electrical field. Now, when the fish swims in, the two people up here have got nets. And as the fish comes along and hits the field, they lock up. And they float to the top, and they're paralyzed, and you scoop them up in the net, and you put them on the dry well on the boat, and you can tag them and do all kinds of things. The most interesting part of this, and we did this at Atwood Lake, beautiful, beautiful. Evenings at Atwood Lake with the electrofishing boat. Wouldn't trade it for the world. You scooped up those fish, you put them in the dry well. Now every night before we went out, the biologist would do some measurements on the lake and then say, put on 7 electrodes, put on 10 electrodes, put on 5 electrodes, and would tell us how many of these little probes we were hanging on the boom. What made the difference?
The concentration of other things in the water.
Bingo. The concentration of electrolytic substances dissolved in the lake. So if the water level was really high, if we had had a lot of rain, but it had had some time to settle and there weren't a lot of things suspended in the lake, then you would have more water, fewer particles, you would put on more electrodes. After a good rain, when a lot of things were still suspended in the water, and you've got more things to conduct, you would put on fewer electrodes. Because you don't want to kill the fish, you just want to stun them enough to get them into measure. You were looking at the lake as a big electrolytic solution, which they are. Okay, so factors that affect rate of dissolution. If you were making Kool-Aid with old chunky sugar, what's the first thing you do? You break it up, you use your wooden spoon and you chop, 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 chop. All you're doing is increasing the surface area of your solute that's being exposed to your solvent. So if we imagine a chunk of salt, and here's our chunk of salt, bunches of sodium and chlorine held together, bound together by forces of mutual attraction, and it's got a surface, right? So which atoms, which ions are exposed to the solvent? Only the ones on the outside, right? The solvent is the liquid in a liquid and solid thing. So the solvent is the thing that does the dissolving. The salt here would be the solute. What if we break this cube in half? Now, this one and this one that were not previously exposed to the solvent are now exposed to the solvent. So changing the surface area exposed to the solvent speeds up getting something dissolved because you're exposing more of the material to the solvent. Okay, the other thing, how many of you make Kool-Aid by putting the sugar and the Kool-Aid powder and the water in a pitcher and walking away from it?
Wait, what?
You just walk away? Just leave it? Wait until it gets itself all mixed up? What do? You stir it. Because when you stir it, you're adding what to the system? Energy. You're adding kinetic energy to the system. You're moving the molecules. And when you move those molecules, that energy allows the solvent to more effectively dissolve the solute. Okay, so agitating the solution will also increase the rate of dissolution. Any of you know the hot water Kool-Aid trick?
Yeah.
What do you do? Yeah, if you put warm water in it and stir it, your sugar dissolves much faster, because heating up a solution as you dissolve something in it will also increase the rate of dissolution. And that's because when you heat it up, what are you doing? Adding what to the system? Energy to the system. So same thing as by stirring, but by a different mechanism. You're actually speeding up the particles. And so you're increasing the number of collisions, you're increasing the rate at which it can dissolve. So, stirring, heating, changing the surface area. Those are all good ways to speed up dissolution, but there are limits. So for any solution we can think of, there are limits to how much solute we can get to dissolve. And that's usually listed in something like grams per liter as a measure of concentration. And it varies by temperature, because at a higher temperature, of course, you have increased solubility. So we have our little sugar solution going on our heating and stirring plate. So we can put X amount of salt in here, or sugar, or anything else we're going to dissolve in. And there comes a point where we can't put any more in. There are limits to solubility. But before we reach that limit, we have solution equilibrium. Of course, you knew we'd talk about equilibrium. We talked about it with regards to phase change. So if we have a solution, and here's a chunk of solid sodium chloride, and we have our little ions all around it in solution, they're moving randomly. Every now and then, one of these ions is going to hit the solid. What's going to happen when it does that? That solid's pretty attractive. They're going to get stuck. They're going to end up, we call it recrystallizing. They come out of solution. And at the same time, that water is moving around the solid, and so some of these particles are going to come out of solution.
So is that what you put too much in?
No, not yet. So it's a dynamic state, but solution equilibrium is when those rates are equal. When we have equal numbers of particles coming out of solution, going into solid, going out of solid, coming into solution. And that's a pretty simple idea. Now we're going to talk about if we have as much stuff as we can possibly get to dissolve in a solution, we call that saturated. And this sugar solution that we're making is probably pretty close to saturation. We're going to push that saturation level by heating it, which we're doing. When a solution can't take any more solute, it's saturated. Until that point, it's unsaturated. Tomorrow we will talk about supersaturated solutions and rapid crystallization.